Hello everyone, Dr. Hasbullah here, and in this video we are going to be looking at dimensional analysis. Now, in studying the physical world, very often that equation alone is not enough to describe everything, and therefore from time to time we do need to conduct experiments. Even sometimes when we found equations based on theory, we do need to verify that equation using experiment. And usually in conducting experiments, we often have two types of variables. First is called dependent variable and the second one is called independent variables. And of course, we are interested in looking at how this dependent variable change if we change these independent variables. Now, let's say that we have one dependent variables and one independent variables. What you would do is you would plot this graph and look for the relationship between the dependent variables and independent variable. Maybe the graph looks something like this. But the problem is, let's say that you have 5 independent variables that defines this one dependent variable. How would you do that? That would make our experiment becomes very complicated. For example, if I want to assume that a pressure drop across something is depending on the flow velocity, density, viscosity, diameter, and also gap height. Okay, now you have about 5 independent variables that defines the dependent variable. Now, let's say that you want to conduct an experiment, and the first thing that you need to do is you need to fix these 4 parameters, right? And then you would obtain the relationship between delta P and velocity. You would change that velocity, okay? And then if you are looking for the relationship between delta P and the density, then you would need to make other variables constant. And of course, the next one, if you want to figure out the relationship between pressure drop and viscosity, for example, you're going to have to keep another 4 variables constant. Now, it may be possible for you to control, for example, velocity, diameter of the pipe, and also height. But what is so difficult to control, for example, is density and viscosity. Imagine if you need to find a fluid that has constant density but variable viscosity. That's going to be difficult, isn't it? And then, could you find fluid that has similar viscosity but has different density? It could be very well impossible. So in order to solve this problem, what researchers have done is that they group these variables together and form what they call dimensionless parameter. So dimensionless parameter is basically a group of these dependent and independent variables. For example, let's take a look at this pressure drop example. When you group this together, what you have is, in the end, you will have delta P over rho V square equal to the function of V rho D over mu and H over D. As the name suggests, these are the group of parameters that when combined to each other have no dimension. A very straightforward example is here. H over D is simply length over length. Okay, so it has no dimension at all. And when you have this kind of relationship, when you conduct experiments, you no longer have to test for each variables. What you need to do is just plot a graph of delta P over rho V square against V times rho times D over mu, and then plot the graph according to the ratio of H over D. Say this is H over D1, this is H over D2, and H over D3. And that's it. You only have to plot this one graph and you have actually figured out the relationship between this pressure drop against these independent variables. But of course, you do not do it individually. You do it in groups. And this is why dimensionless parameter is very important in experimental work. And if you notice here, this group of variables is simply called Reynolds number. And now that we know how powerful these dimensionless parameters are, the challenge now is to group them together. How would you select what parameters to be grouped to each other in order to form a correct dimensionless parameter. In order to do so, we're going to use a technique that is called the Buckingham-Pi Theorem. Let me write it here. So this is Buckingham-Pi Theorem. Now, Buckingham-Pi Theorem is basically a set of instructions that you can follow step by step in order to form a dimensionless group from a number of variables. And to make this easy on you, let's just work on an example. Okay, we're going to find a parameter that contains one dependent variable and a few independent variables, and see how we can use Buckingham-Pi Theorem to obtain these dimensionless parameters. And now the example that I'm going to be using is drag force. So drag force Fd is a factor of diameter, length, velocity, viscosity, and density. Now you may ask, how do I know about these variables? And the truth is, in the real world, it is very difficult for researchers to know what exactly are these independent variables. And they obtain this usually by a very long research experience. They have determined what parameters are important, what parameters are not important from their previous experiments, so that they can conduct a new experiment using these new variables. So at the moment, you do not have to worry about how to find these independent variables. Your task now is how to group these dependent and independent variables together so that you can form dimensionless parameters using Buckingham-Pi Theorem. So let's try and do that, shall we? So the first step is to list all the variables and its dimension. So list all variables and its dimensions. So let's do that. And we have here Fd, and then we have diameter, we have length, we have velocity, we have mu, and we have rho. So for Fd, what is the dimension for force? And remember, I'm looking for dimension, not unit. We know that the unit for force is Newton, but the dimension is, so force is mass times acceleration, and acceleration is distance over time square. So the dimension would be, this is m, distance is length over time square. So the dimension for Fd is m length over time square. Or you can write it as mLt minus 2. It is up to you. And of course, the diameter, the dimension is length. Length, of course, dimension is length. Velocity is length over time, isn't it? So this is L over T. Viscosity is a little bit tricky. So we have here tau equal to mu du over dy. So mu equal to tau times dy over du, and tau is basically force over area, and force is that. So this is ml over t square. Area is simply length square, and then dy is length and du is length over time. So you end up with, cancel out t, cancel out l, this is simply m over lt. Okay, so I'm going to write it here, m over lt. Density is simply mass over length cube. And I need you to practice this. Basically, try to find the dimensions for any variables that you can think of. This will be a good exercise for you so that in the examination, for example, you can think very quickly and this is all seem familiar to you. Okay, now let us move on to the second step. And for the second step, what you need to do is you need to find the value of pi. And pi is equal to n minus m. Okay, now let me explain to you what is n and m. N is simply number of variables. And in our case, the number of variables is 1, 2, 3, 4, 5, 6. So that will be your n. Simple enough, right? So n is 6. And what about m? M is the number of dimension. The dimension that we have for all these variables. is either m, l, or t. So your m value is 3. Okay, I'm going to put this here 3. So pi is 6 minus 3, and therefore the answer is 3. And what does this pi equal to 3 means? Pi equal to 3 means that in the end, when you have these dimensionless parameters, what you have is pi 1 equal to the function of pi 2 and pi 3. And each pi contains the variables that when you combine them together, produce the dimensionless parameter. Okay, don't worry too much yet, but let's now move on to step number 3. And for step number 3, you need to find what is the repeating variables. Okay, repeating variables, as the name suggests, are the variables that repeats for each dimensionless parameter. For example, let's take a look at our earlier example. For example, this one. Okay, and let me mark the repeating variables. Okay, so if you notice here, density is the repeating variables because it exists in a few places. And what else? I think velocity is also repeating variables. And diameter is also repeating variables because it exists at multiple places. And there are a few rules that you need to follow in order to determine these repeating variables. So the first rule, which is very obvious, is that the repeating variables cannot be your dependent variable. So in this example, delta P cannot be repeating variables because this is your dependent variables. It cannot exist at multiple places. It must exist as the title of that equation. So let's take a look at our example. So FD definitely cannot be your repeating variables. Okay, so I'm going to cross it here. FD cannot be your repeating variables. Okay, now let's list the rules for finding repeating variables. So repeating variables must be independent variables. The next one is, how many variables should we choose to become repeating variables? The answer is, repeating variables must have m number. Okay, so in this case, in our case, m is equal to 3. So our repeating variables has to be 3. And the next rule is that the combination of these 3 repeating variables must contain all the dimension. So in our case, it must contain length, must contain mass, and must contain time. Okay, so let me write the rule here. This has to contain all dimension. And finally, the combination of these repeating variables, however configuration that you decide, cannot form dimensionless parameters. Okay, let me write that first before we go to our example. So, cannot form dimensionless parameters by themselves. Therefore, what these rules mean is that, let's take a look at our variables here, and let's see what we can select in order to fulfill all the rules. Okay, now I'm going to select D, and I'm going to select velocity and density. Now we're going to see how this diameter, velocity, and density falls into the rules that we have listed before. Okay, so my repeating variables are D, velocity, and also rho. Now let's take a look at the dimension for each variables here. This is L, this is L over T, and this is M over L cubed. Okay, so the first rule says that this must be independent variable. So that is sorted. Now must have 3 repeating variables. So of course we have chosen the 3 repeating variables. Has to contain all dimension. Now it contains L, it contains time, and it contains mass. Okay, so this satisfies the rule number 3. Now finally, the combination of these variables that we have chosen to be repeating variables cannot form dimensionless parameters by themselves. Meaning that because I have L, I have T, and I have M here, can you see that no matter how I try to combine these variables together, maybe I can find a way so that in the end, this L cube can cancel out because L also exists here and here. But I would never find a way to cancel out the mass and also the time, because mass only exists for density and time only exists in velocity. So there's no way to cancel them out by combining these three parameters. And that means that this combination satisfies our rule number 4. Okay, now let's move on to our step number 4. Step number 4 is form the pi terms. And how do we form these pi terms? We know that we have 3 pi's, so pi 1, pi 2, and pi 3. Now, because we have chosen d, v, and rho as our repeating variables, what's left is fd, L, and mu. So, for our first pi, it's going to be fd equal to fd, and that's got to be to the power of a, and followed by our repeating variables. So, repeating variables are d to the power of b, v to the power of c, and rho to the power of d. Later, you will see what we do with this A, B, C, D. Okay? And right now, just follow the same step. So, for pi 2, you have here L. So, we're going to combine that. L to the power of A, D to the power of B, V to the power of C, and rho to the power of D. And finally, for pi 3, we have one more left. This is mu. So, mu to the power of A times d to the power of b, v to the power of c, and rho to the power of d. And of course, our job now is to find what is a, b, c, d, and we will be done. Okay, now let's take a look at how do we find it. Let's do it one by one. So let's do pi 1 first. So pi 1 equal to, this is fd to the power of a, d to the power of b, v to the power of c, and rho to the power of d. Now, what is the dimension of fd? So fd is ml over t square. I'm going to write mlt minus 2. mlt minus 2 is going to be to the power of a. D is length to the power of v. Velocity is length per time, right? This is lt minus 1 to the power of c. And finally, rho is mass over length cube to the power of d. And this must all equal to non-dimensional. Okay? So m to the power of 0, L to the power of 0, T to the power of 0. And this is how we are going to find our A, B, C, and D. Let's do m first. Okay? Now, m to the power of A, so this will be A. And the next one is m to the power of D plus D equal to 0. Let's do L. So L first is L to the power of A plus L to the power of B plus L to the power of C plus L to the power of 3D. And I think we may have made a mistake here because density is ml minus 3, isn't it? So this is minus 3. So this is actually minus 3D equal to 0. And finally, we have T. T is here, minus 2A. And the other T is minus 1C or minus C equal to 0. And therefore, what we need to do now is just to solve this equation in order to find what is the ABCD. So from here, A equal to minus D. And from here, we have C equal to minus 2A. And let's try to solve this equation. So A plus B plus C, but now C is minus 2A. So minus 2A minus 3D, but D is equal to negative A. So this becomes plus 3A equal to 0. So what we have here is b plus 2a equal to 0, which means b equal to minus 2a. Right? Of course, we cannot solve it yet because if you notice, we have 4 unknowns but only 3 equations. But don't worry, we can still solve this. And if you think about it, okay, let's take a look at a. Right? For dimensionless parameters, we understand that there will be no dimension. So it doesn't matter if you have L over L or if you have L square over L square, it will still have no dimension, isn't it? So let's do a equal to 1, shall we? So if we do a equal to 1, we will have b equal to minus 2, and we're going to have c equal to minus 2 as well, and we're going to have d equal to minus 1. And let's see how this works out. And I'm going to write pi 1 again. So pi 1 equal to f d to the power of a, d to the power of b, v to the power of c, and rho to the power of d. Now, a is equal to 1. So fd and b, c, and d are all negative. So it should be down here. Now, for diameter, my b is negative 2. So this is diameter square. And velocity, my c is negative 2. So this is velocity square. And my density is to the power of d, and d is minus 1. So this is rho. Okay, and if I rearrange this properly, so pi 1 equal to fd divided by rho d square v square. And we can now be confident that this term is non-dimensional because we have zeroed all the dimension here. And if you notice, if you are not satisfied with Buckingham-Pi Theorem, you are always welcome to check it again. Okay, you can simply list what is the dimension for fd, what is the dimension for rho, what is the dimension for d and v, and really check if this group is dimensionless. So now pi 1 is done, and remember, the final form is pi 1 is a function of pi 2 and pi 3. So we still need to find pi 2 and pi 3. Now finding pi 2 and pi 3 is going to be straightforward because we already find pi 1. And the steps are similar. Now let's take a look at how to find pi 2. First of all, pi 2 is L to the power of A, d to the power of b, v to the power of c, rho to the power of d. And let's just do it again. So for L, the dimension is length to the power of A. Diameter, also the dimension is length. This is to the power of B. Velocity is length over time. So LT minus 1 to the power of C. And rho is mass over length cube to the power of D. And this is equal to M0, L0, T0. Let's do M. Now it's quite simple because M only have D, so this is definitely 0. L has A plus B, so you have A plus B plus C minus 3D plus C minus 3D equal to 0. So usually for L, you will have all of the A, B, C, D because length is a very common unit, right? Now, finally, you have T, and we have here T equal to minus C, and that's it. This is also equal to 0. So D and C is 0. That makes it easy for us to cancel this out. D and C is just 0. So A plus B equal to 0, meaning that A is equal to minus B. So it doesn't matter. A can be 1, B can be negative 1, or A can be 2, B can be negative 2. It doesn't matter. So let's do A equal to 1. And you end up with pi 2 equal to L to the power of 1, d to the power of minus 1, v to the power of 0, and rho to the power of 0. So you end up with L over d. Now because this is simple, you can clearly see that if we consider A equal to 2, for example, okay, A equal to 2, you will end up with L square over d square. And what's the point of this? This is dimensionless. So to make things clean, just do A equal to 1 and you end up with L over d. Okay, now finally we have pi 3, and pi 3 is equal to mu to the power of A, D to the power of B, V to the power of C, and rho to the power of D. And for mu, the dimension is, good for us that we have listed here the dimension. So this is m over LT, L minus 1, T minus 1 to the power of A. D is simply length to the power of B. V is length over time to the power of C. And rho again is mass over length to the power of 3 of D equal to M0, L0, T0. Okay, let's carry on with M. Now you have here A plus D equal to 0. And next you have L. This is minus A plus B plus C minus 3D equal to 0. And finally you have T, which is minus A minus C equal to 0. So let's solve for this. A equal to minus D, and A here is equal to minus C. And this effectively means that D equal to C, isn't it? So if we want to solve for this, and let's make everything D. So minus A is D plus B plus C, C is D. And minus 3D equal to 0. So this will be B minus D equal to 0. And B equal to D. And again, let's just do A equal to 1. Because why not, right? So when A equal to 1, B is going to be equal to D. D equal to C. C equal to minus A. B equal to minus 1. C equal to minus 1. And D also equal to minus 1. So we end up with pi 3 equal to mu to the power of A is 1, D to the power of B is minus 1, V to the power of C is minus 1, and you have here rho to the power of D is also minus 1. And you end up with mu divided by rho times velocity times diameter. So there you go. Pi 1, pi 2, and pi 3 is now done. And the final step is just writing the dimensionless parameters. And that will be step number 5. Writing the dimensionless parameters. Okay, and dimensionless parameters is simply pi 1 equal to function of pi 2, pi 3. Now our pi 1 is Fd over rho d square v square, Fd over rho v square d square equal to the function of our pi 2 is L over d, and our pi 3 is mu over rho times velocity times diameter. Right, and this will be your final answer. This is the dimensionless parameters. But you could actually make this cleaner, okay? And this shows that you actually know what you are doing, because mu over rho v times diameter is actually 1 over Reynolds number. Okay, so why not we make it Reynolds number? Because if it's 1 over Reynolds number or Reynolds number, it doesn't matter because this is dimensionless. Okay, so we can also write the function of Fd over rho v squared d squared as the function of L over d and Reynolds number. So this looks cleaner, isn't it? And I think our L here, I may have accidentally changed it. This is actually small l, not the capital L. Okay, so let me change this. So this is actually small l. Okay, and that's it basically. That is the Buckingham-Pi Theorem. And if you notice, Buckingham-Pi Theorem is just a set of rules or steps that you need to do in order to group a lot of variables together so that they forms dimensionless parameters. And these parameters you can later use to perform your experiments. Okay, now of course I think that this video is getting a little bit too long. So what I need you to do now is to look for an example in your textbook or just an example online and try to perform this Buckingham-Pi theorem on another parameters. Okay, we just did the dimensionless parameters for the drag force. Maybe you can go and look for something else and run over this step again and go through these steps of Buckingham-Pi theorem again and see if you can successfully combine the parameters together to form a complete non-dimensional parameters. Okay everyone, that is all from me for now and I'll talk to you soon. Bye!